Um, I have posted the solutions, so you can look at those outside my office if you choose to. Regarding what a plus, check, or minus might mean, if you've attempted the majority of the problems and your methods are generally correct, then you would have gotten a plus. If you didn't do a certain number of the problems, maybe only 2/3 of the problems, or if you perhaps didn't do all the problems but then some of your methodology was off, I would have given you a check. I figure a plus is maybe 80 to 100%, a check is perhaps 50 to 80%, it's kind of something like that. A minus would mean that you've done less than half the work, or that you have problems throughout with methodology. I've got so many students this quarter in my 3 classes, I have no time to really accurately grade the homework, but if there's something that I saw right away or something that's obvious, I made some note of it on your homework that's being returned to you. Most of you did fine. There were several of you who had a few issues here and there. For instance, some of you weren't reading problem 139 too carefully. It talked about a temperature change of 45 degrees. And note that a temperature change is not the same as an actual temperature. A temperature change in Rankine would be exactly the same as a temperature change in Fahrenheit. You divide it by 1.8, so a temperature change in Celsius, so a temperature change in Kelvin, or 25 degrees. Those are exactly the same. Problem 145, some of you didn't notice that it was a vacuum gauge, so that the gauge pressure is actually negative 35 kilopascals, so you add that negative onto the atmospheric pressure of 92, so you get 57 kilopascals, so that was a pretty common error. Most of you did the pressure cooker problem okay, but please recognize that you draw a free body diagram on the little petcock on top, and it would have a weight term and an atmospheric pressure term forcing downwards, and then there's a pressure from the pressure cooker acting upwards. Note that the pressure cooker has a gauge on it. When they tell you 100 kilopascals, that's the gauge pressure, that's not the absolute pressure. So the pressure on the inside of the pressure cooker, it reads 100, but it's really 100 plus 101. So 201 kilopascals is the pressure on the inside. So that was another common error. Anyway, I just wanted to point out those few things. You're certainly welcome to look at the posted solutions for more information. By the way, a balance beam scale really just is a mass balance scale. It has nothing to do with the weight. If you have a spring scale, well, that's different. Then you're dealing with the weight. So there's that one problem where it talked about a scale on the moon. If you're using a spring scale on the moon, then your weight would be a lot less than what it would be on Earth, like 25, 26 pounds. On the other hand, when you use a mass scale, a balance beam scale, the weight would be the same. So if it's 150 pounds on the Earth, that mass would give you 150 pounds on the moon. Anyway, any questions on the homework? All right. Put that aside. Just a reminder that Monday is your Martin Luther King Jr. birthday holiday, so no school that day, so I'll see you Wednesday. Remember that your homework set number 2, which includes some problems from chapter 2 and 3, are due when I see you next Wednesday, so please don't forget to bring the homework with you then. All right, so let's just go back to where we were last time. We're beginning to get a better feel for the nature of thermodynamic properties. We understand that pressure, temperature, specific volume are really the 3 most commonly used properties because, frankly, they're all measurable properties. If we remember that for any simple compressible system, any 2 intensive properties, which would include temperature, pressure, and specific volume, if we know any 2 of those properties, then that sets the state. Knowing any 2, all the other properties are known to us. With that in mind, we can pretty easily look at a drawing that relates some of these properties. Now, I actually put a general temperature pressure diagram on the board last time, and that's where we saw the distinct regions. We understand that each phase is shown, the solid, liquid, vapor phases are shown, and we would also understand that there's a line between those phases, which is really a 2-phase region, where at any one particular pressure and temperature, you can have all vapor or all liquid or anywhere in between, or at maybe another pressure and temperature, we could have all liquid and all solid, or a mixture of any of the 2. So what we have to recognize at this point is that we're not really interested in solids for most mechanical processes. We're really interested in liquids and vapors. So what makes more sense is for us to kind of key in on that one section of our temperature pressure diagram, which includes the line where we have that phase change, right? The saturation region, if you will, would be shown on a TV diagram like this, but if we just look at a temperature pressure diagram, it's just a single line, and that's our vaporization line, right, where the liquid turns into the vapor. But we're interested in processes that involve a change of phase, liquid to vapor and back again. We want to know how other properties, not just temperature and pressure, are related to each other. So it's very common to have a temperature versus specific volume diagram. And this is really what I talked about at some length at the end last time. Let's keep in mind that inside the dome, if you will, we call this the saturation region. We saw this last time. Anything on the right-hand side is the saturated vapor. Anything on the left-hand side is what we call a saturated liquid. The critical point is up on the top. Anything to the right of the saturated vapor line we just call superheat, or more specifically, superheated vapor. Anything to the left is compressed, or more specifically, it's a compressed liquid, or also called a subcooled liquid. But these are the regions that we're primarily interested in. When we solve a problem, like our power plant, like our air conditioner refrigeration cycle, or just any individual process, like a pump or a turbine or a heat exchanger, any of these processes are going to be shown on this kind of a diagram. We're going to see a relationship between different properties. Certainly it makes sense to us. Let's just say we're talking about boiling water into steam. We know that when we boil water into steam, the temperature doesn't change, at least at standard atmospheric pressure. It's going to be 100 Celsius exactly. But when we first begin the boiling process, we're over here at the saturated liquid line, and it's all liquid. When we're finished, we're going to end up with all vapor. The pressure is still atmospheric pressure, the temperature is still 100 Celsius, but certainly we've changed the volume quite a bit. So note that this horizontal axis is specific volume, this is not total volume, and that's what's being shown here. Another thing that should be shown is what would a constant pressure line look like on this type of a diagram. And again, it doesn't matter whether we're talking about water into steam, or whether we're talking about a refrigerant, or something like propane, or any other pure substance. All substances behave the same way. The scales are going to be different, the numerical values are going to be different, but they behave the same way. If we look at a constant pressure line, then a constant pressure line on this kind of a diagram would look like this. So it slopes rapidly, both in the compressed liquid region and in the superheated vapor region. But this is a line of constant pressure, okay? And it should be noted that pressure increases if we move further up. So, you know, if we had higher pressures, this would be at a higher pressure. So I'll just put increase in P is going to be in that direction. Well, I suppose say increased pressure. Okay. Now, if you think about it, it makes sense, right? I mean, if we think about, let's say, atmospheric pressure versus, let's say, the pressure in the mountains. We know that the pressure in the mountains is less. So if this, you know, heavier line, let's say, just represents standard atmospheric pressure, you know, again, just as an example, we know that for water, this temperature here has to be exactly 100 degrees Celsius. Again, if we're talking about water and pressure at one standard atmosphere. Okay. On the other hand, if we're up in the mountains, we know that the pressure is less, right? So our pressure is going to be down here somewhere, and the temperature clearly is also going to be less. Yes?
Was the small v and gamma interchangeable?
This is only a small v. If it looks like a gamma, then that's me not writing very clearly. Yeah, this is specific volume on this axis. Yeah, we haven't even used any gammas yet, so I'll let you know when we get there. Anyway, temperature and specific volume, right? Right. So again, we can see that as the pressure rises, like if we're, say, in Death Valley, several hundred feet below sea level, water boils at a higher temperature. If we're up in the mountains, we know the water boils at a lower temperature. So, I mean, this kind of a diagram should make sense to you. Another thing that should be noted is that it's also common to show pressure versus specific volume. There's still going to be the characteristic dome with a critical point up on top. In this particular case, we still have our saturation region in the middle. But if we were to draw a line of constant temperature, it would go like this. They would drop pretty rapidly in the compressed region and then, again, pretty rapidly in the superheat region. So this would be a line of constant temperature. And then, temperature is going to increase if we go up this way. Again, the scale is different depending upon the substance we're talking about, but the reality is this is the way that all substances behave. Okay, now one thing I also mentioned last time has to do with what's called the quality. Remember I had defined at the end that quality is the mass of the vapor divided by the total mass in a two-phase mixture. Okay? So if the quality is very high, that means it's mostly vapor, mostly steam in a steam water vapor mixture. So anything closer to the right-hand edge of the dome is going to be high quality. Anything closer to the left-hand edge of the dome is going to be of low quality because you can see that you're mostly the saturated liquid portion of the two-phase mixture. The right-hand side is mostly the saturated vapor portion of the two-phase mixture. And keep in mind that when it's a mixture of the saturated liquid and saturated vapor. There's nothing that exists truly in between. I mean, there will be, let's say, an average specific volume based upon how much of it's liquid and how much of it's vapor. But that two-phase mixture is a mixture of the saturated liquid portion and the saturated vapor portion of that mixture. Right. So anyway, back to the idea of quality. Maybe you could see that if we have a saturated liquid, and I always just use SAT as an abbreviation for saturated. Saturated liquid means we're on the left-hand side of the diagram. It doesn't matter which of the two diagrams, but still we're on the left-hand side of the diagram. So if we're right on the saturated liquid line, that means that there's no vapor. And in fact, it's not really even a two-phase mixture. There's just one phase, but we can say that the quality is equal to 0. If we were to add even the tiniest bit of heat, then some water molecule will turn from a liquid to the vapor phase, and then we will indeed be a two-phase mixture, mostly liquid, certainly at a very low quality, but a liquid-vapor mixture nonetheless. Now, if we add heat all the way into the point where we finally vaporize that last little bit of liquid, we would call that the saturated vapor. These were identified on the drawings in your notes from last time. But nonetheless, if you have a saturated vapor, that's as much vapor as you can have in a two-phase mixture. Technically, it's not really even a two-phase mixture. It's all vapor, but anything on the right-hand edge on the saturated vapor line, we can just say that the quality is 100%. We can also say that it's 1.0. We can write it as a percentage if we choose. It's really up to us. All right, so when we're solving problems, we're certainly going to solve problems that are in the two-phase region or right around it. Some is going to be compressed liquid, some is going to be superheated vapor, sometimes it will be all sat liquid, sometimes all sat vapor, sometimes a mixture of both saturated liquid and vapor. But at least we understand that this diagram gives us a feel for what's happening for our processes. Now, when we finally get to the point where we're solving real problems, yes, I'm going to have some sort of a physical sketch that shows my tank, my pump, my turbine, whatever, but it's also really important to have a thermodynamic property sketch like the TV or like the PV diagram. There's others we'll look at, but this just gives you a feel for what's happening from a thermodynamic point of view. Consider that there's going to be a lot of problems we're going to analyze where something stays the same. Like maybe we've got a fixed rigid vessel. The mass isn't changing, the volume isn't changing, therefore the specific volume isn't changing, right? Specific volume is just volume over mass. So if you've got a sealed rigid tank, it's a constant volume problem. No matter what you do to that tank, no matter how much energy you transfer to or from, you still end up with the same specific volume because neither mass or volume is changing. So you'd have a problem that would be a vertical line on one of these diagrams. Other problems, maybe you have a constant pressure problem, like one of these frictionless vertical piston cylinder devices we talked about before, right? If the weight of that piston and the area that it acts through is constant, then the pressure is constant. It doesn't matter how much heat you add, how much work is done, what properties change. One property, pressure, is certainly going to remain constant. So if you have a nice PV diagram, you can show a process like that just with a horizontal line. So we can use these diagrams to just give us a clue as to what's happening within the problems at hand. So these thermodiagrams are really, really quite important. So this at least illustrates how we can use a diagram to show the relationship between properties, right? If we know any two properties, like say pressure and temperature, or pressure and specific volume, or temperature and specific volume, we should be able to go onto a diagram like this one with the appropriate scale for the appropriate substance, of course, and read off whatever the other property is we're looking for, right? And this is just pressure, temperature, and volume. There's all those other properties that we've talked about that are not measurable, like entropy and enthalpy and internal energy. We could just as easily show a temperature versus internal energy, or a pressure versus an internal energy diagram, or temperature versus enthalpy, or temperature versus entropy. We can put any diagram together we want, but we understand that knowing any two properties, we can come up with all the rest of the properties. Now, does that mean that we're going to have to use diagrams like these that I've shown you here to get the actual thermodynamic property data for the processes at hand? Well, the answer is no. There are certainly some diagrams that are in your book. There's a famous diagram called the Moyet diagram, which is actually an enthalpy versus entropy diagram. There is a copy of that in your textbook. And if you learn how to use one of those, then knowing any two properties, I mean, it's an enthalpy-entropy diagram, but it has lines of temperature on it, and lines of pressure on it, and lines of specific volume on it. Some even have internal energy on them. You can just go to a diagram and use the diagram to find the other properties we need. So the question we now really want to ask ourselves is, where is our data? In other words, knowing any two intensive and, of course, independent properties, how do we find the others? So that's what we have to ask ourselves now. Now, there's many different ways to do this. And this, in many ways, is the hard part of this class, is just knowing for any particular problem, what kind of data do you have available to you, and then how do you use it? How do you use it accurately? So there's really three choices. We can have graphical data. So again, this Moyet diagram that I mentioned before is enthalpy versus entropy with other properties shown. So we can just go into that, and knowing any two data points, read the rest. Not always practical. Another way to do this is by the use of tables. So data has been collected in laboratories. It's been correlated, and it's been put into tabular form. So this is another common way to get data. And again, this has nothing to do with the processes or how to use the first law of thermodynamics. We're only now talking about basics still. At this point, we're specifically talking about where do we get our data from? How do we use it? Eventually, all this will come together, and we'll see how to solve real problems. Okay, so graphical means, tabular means. Another one would be by use of equations. So these are empirical equations that are developed after lengthy research. Now, which one of these do we really want to use? Well, we use what's ever available to us. If you really want to know the truth, in this modern world of ours, since everything is all computerized, there's computerized databases of absolutely everything. If you're clever or persistent, you can go online and you can find somebody who's published an electronic version of the tables that we're going to actually use most of all. These are called water tables or sometimes just steam tables. But equations do exist, so that's often something that we do, although we don't use it a lot in this class. Graphs certainly exist, tables certainly exist. Well, what are we going to use? Okay, so I will note that most of the time we're going to use tables. Okay, and we've got various tables that are in your book. We will use equations sometimes. Graphs, not a lot, a little bit for one particular type of problem we'll go to next week, but most of the time it's going to be tables. So now we have to ask ourselves, well, where are these tables? What are they used for? So let me just give you a summary of all these various tables that you have available. And then we're going to start going through problems, just examples to show you how to use these tables to find data. Once you get good at that, then we'll start looking at real problems. All right, so what about the tables? Let's just go back to, we won't go back anywhere. I think I've got space here. Okay. So there's two sets of tables that are particularly useful to us. One for water and the other for a particular refrigerant. Now, if we want data for the saturation region, we would go into table A4 or A5. Okay? These are both saturation tables. Okay. And the only data that it presents is data for saturated liquids and saturated vapors. If you have a two-phase mixture, well, that's okay. We would use what we call quality, right? And that'll tell us how much of it's saturated liquid versus how much of that mixture is saturated vapor. But table A4 and A5 are saturation tables, and we'll look at these tables here shortly. Okay. Oh, by the way, you might wonder, well, why are there two tables? Turns out that table A4 is listed in uniform increments of temperature, and A5 is in uniform increments of pressure. It gives you the same data. We should certainly understand at this point that whenever you have a saturated mixture, whether it's all saturated liquid or all saturated vapor, pressure and temperature are not independent. So for any one value of temperature, there's only one possible value of pressure on these saturation tables. For any one possible value of pressure, there's only one possible value of temperature. It just happens that A4 is in nice uniform increments of temperature, A5 is for pressure. When we move on to A6, A6 is superheat. So this is superheated vapor. And table A6 is actually a whole series of subtables. So for the full range of pressures that we might ever see water for, we'll have a table at one pressure, and then all the data will be in that table, call it a subtable. Then we'll have the next higher pressure, and it'll be another subtable. And again, we'll look at all this here shortly as well. So this is superheated vapor, and it's actually a series of subtables. Okay, and then A7 is for compressed liquids. However, there's a big problem with table A7. I don't know why the author even bothered to put it into the book in this form. It's also a series of subtables, but the lowest pressure subtable is such an incredibly high pressure that it's a pressure that we never even see, at least generally don't even see in any kind of real application. So while the table is accurate, the range of the data on the table is higher than anything we're really ever going to use. So the compressed liquid table exists, but it's basically out of range for most of the problems that we're going to use. So there's actually a way that we can approximate data for a compressed liquid. And again, this is something that we'll be talking about, today. Okay. So tables is what we use. Now, what if we don't have water? Are there other tables? Sure, there's other data in there. I'll just continue this down below here. There's one refrigerant, R stands for refrigerant, And that refrigerant is refrigerant 134A. That is the only refrigerant where we have data. And we have something quite similar to what we have above here. A11 and A12, these are the saturation tables. This should say 11. A11 is a saturation table listed in uniform increments of temperature, 10, 20, 30, 40, 50. Whereas A12 is still the saturation tables, but it's in uniform increments of pressure. So just like water, we have both the pressure and the temperature tables. And then A13 is superheat. So this is superheated vapor. There is no compressed liquid table. And again, I have no idea why the author didn't do this. Certainly we use compressed liquid refrigerants at times, but there is no compressed liquid table. So that's it. Again, if you have a compressed liquid, you are going to have to use an approximation that I have yet to discuss with you. Okay. So this is where you're going to get your data for your various tables. Maybe now would be a good time to actually look at these tables and get a feel for what kind of data is there and also how to use it. So let's see if this works. So basically what I've done is I've taken the various tables and figures that are in the appendix of your book, and I've put them together, and that's something I'll probably pass out during exams. Especially if it's a closed book exam, you're still going to have to use your property tables. So this is just a copy of that same thing, my little index. But let's just move on. In fact, let's just go through it slowly. Table A1, and hopefully, well, I see it back there. Okay. Okay. We'll get there eventually. If you want, you look at the tables on the back. Yeah, I don't know. Okay. So we're working on it. Okay. Now none of them work. Well, yeah, I just don't want to spend too much time waiting. I did ask you last time to either bring in your textbooks or to have your laptop or something available. So, if for some reason we're not able to get this to work properly, then I might just have you kind of look in your own individual books. Maybe a loose cable. Well, I guess we can be patient for the time being.
I'll try to get there restarted, but if anything, it's back there.
Okay. Well, then maybe what I'll do just to make this easy is to just have you guys just look at the screen on the back for a moment while our technician here is figuring out what's going on. So this is actually table A1. This is not the table I'm immediately talking about. But I will note that last time we talked a little bit about different substances and critical point data, molar mass data. So if you look in the back here, table A1 is just going to give you some of that data. We don't know when or why we're going to use it at this point, but this is the first table. And there's also table A1E. Oh, there we go. So it's working now up in the front. This is a good table just to know about. You will need molar mass data sometimes. You will need critical point data sometimes. So I just want to point that out here. And it gives you all sorts of pure substances. If we go on to table A2, we're not ready to talk about gases yet. That's something that we'll talk about next week. So we can just ignore A2 and A3 for the time being. And by the way, there's an A2 part A, an A2 part B, an A2 part C, and the same thing with A3. There's parts A, B, and C. But let's go on to table A4, which is a saturation table for water. Now, I brought my pointer. It looks like pointers don't exactly work on televisions, do they? Oh, well, somehow I'm supposed to be able to plug this in to the computer. And I don't want to mess with that right now. We'll just look at it. All right, so again, this is a saturation table, right? It says saturated water, and it says temperature table, meaning that this is the table that gives you data for saturated liquid and vapor, but in uniform increments of temperature. So it actually starts at 0.01 degrees Celsius, so just above the freezing point of water. We don't want to deal with solid water here. And the second column is the pressure that corresponds to that temperature. Now again, if pressure and temperature are independent, then at any one temperature there's only one possible pressure. At any one pressure there's only one possible temperature, right? So we use the subscript sat to represent that saturation condition.
What side of it, what you're writing?
I'm sorry. Is that better? So if we use a subscript sat, then that refers to saturation conditions. So on that particular table, table A4, the first column we have is just, what I'd really like to do is keep the computer on the left screen and the notes just continue on the right screen, or right and left. So I don't know what happened there again. Working out the kinks, right? There we go. Good, thank you.
What is that word? Saturated?
Oh, sat just means saturation conditions. So when we have the saturated mixture, if we're looking at, let's say, a temperature volume diagram, we're looking at the saturation pressure that corresponds to that temperature. Okay, so it's just this, if this is a constant pressure line, then whatever this pressure is here that corresponds to our given temperature, we just call that Psat. Okay. So if we have a saturated mixture, whether it's all liquid or all vapor or an actual mixture, then at any particular temperature, it shows the pressure that has to occur at. Then we get to our data. We have specific volume, specific internal energy, specific enthalpy, specific entropy. Before I even move on here, please note that the author is doing what I warned you he was going to do. He forgets to write the word specific here. Note the units on internal energy, enthalpy, and entropy. It's all per kilogram, right? So that's not really the total. Those are specific values. So if you want to just write right into your book or just make a note of yourself, this is lowercase letter v. It does say specific volume, but those are also lower cases. Lowercase u, lowercase h, lowercase s. Those are specific internal energy, specific enthalpy, specific entropy. Now let's just go back over to the left and look at the third column. You can see that it shows the specific volume both for saturated liquid and saturated vapor. So here, the book is going to use the subscript, so another subscript to identify. It uses a subscript F when talking about the saturated liquid, and it uses subscript G when referring to the saturated vapor. So the data in the VF column is just the data here along the left-hand side of the curve, or left-hand side of the dome, right? Anything with the subscript F, that's the saturated liquid data. So at any particular temperature, the book is just giving us data up along the side. And then you go to the next column, right? The next column is VG, so G stands for saturated vapor. And at any temperature, this is just giving us the data down the right-hand side of the dome. So this is where we're going to find our saturation data. For any temperature, we know the corresponding pressure, we know the corresponding saturated liquid specific volume and saturated vapor specific volume. Yes? Okay. All right, so please note that I could have a temperature versus U diagram, or a T versus H diagram, or a T versus S diagram, and the data I have is just the data that rides up the saturated liquid line or down the saturated vapor line. Okay? That's the nature of table A4. Now, please note there's more data, right? There's UF, there's UG. There's also something in between. what is that thing that says evap? It's not saturated liquid, it's not saturated vapor. It has a subscript FG. Hopefully you can read that subscript. If you see the subscript FG, then that's the difference between the saturated vapor and saturated liquid conditions. So the difference between the saturated vapor and saturated liquid. Okay, it's called evap because that is for the evaporation process. What's happening as you go from a saturated liquid to a saturated vapor? You're evaporating, right? You're turning liquid water into water vapor. So for the evaporation process, that is, as you move from a saturated liquid to a vapor, you get another column of data. Now, that data will exist for the other properties as well. You can see that there's a HF, HFG, HG. There's a SF, SFG, SG. Whenever you have the subscript FG, it's the difference between the two properties of saturated vapor and saturated liquid. All right, so it's just something that we need to be aware of. Any questions on that? Okay. The table is not really hard to use. Sometimes it's harder than other times. You know, sometimes you'll be given a temperature and you just go into the table and you read off the other data. But what if you're given something different? Let's say you were given, I don't know, how about the specific volume, and you need to find the temperature. Well, then you have to go into the table and kind of work sideways to find out what would be the temperature or perhaps the pressure that would correspond to that. But nonetheless, this is where all our data resides. And this is the saturated table for water in increasing order of temperature. Yeah.
When you say difference, like as the temperature increases, that difference becomes smaller.
That's true. The difference will become smaller in general because we're getting closer to the top of the dome, and you should be able to see that for essentially any property. I guess you can see the cursor here a little bit, but yeah, the FG numbers are definitely going to be getting small as you go to the higher temperatures. Yeah.
Get a temperature, let's say like it's 27.
Okay. That's something we'll talk about. Yeah, I mean, you can only do so much on a table like this. You are going to have to do some linear interpolation, and I'll give you at least one example of that. So like if you're at 27.5 degrees, you're exactly halfway between 25 and 30. So all of your properties are going to be exactly halfway between the property listed at 25 and the property listed at 30. But sometimes it's not an even number, right? I mean, sometimes you'll have 21.3 degrees Celsius, so you'll have to be a little more clever in your interpolation. But yeah, we do have to interpolate at times, and just accept that. We have to do that. So what about the pressure table? So the temperature table continues onto a second page, and then finally we get to table A5, which is our pressure table. So here you can see, again, it's the same information, right? We have our increasing order of pressure. It starts at 1 kilopascal, and then you have the saturation temperature that corresponds to that pressure immediately next to it, and then you have the data for a specific volume, and internal energy, enthalpy, entropy. Again, these are all specific values as well. So it's just a matter of going into the table at your known properties and reading off whatever data you need. Again, with the understanding that we're still just learning about how to use the tables. Eventually, you're going to have to take data from these tables to solve real problems. If we're solving a problem involving the first law of thermodynamics, we're definitely going to need internal energy data. You might not have internal energy data. Maybe I'll just give you temperature and density, something like that. You're going to have to go into this table and well, that's not really a good one. Yeah, that's a good one. Specific volume is just the inverse of density. So you're going to have to go into this table at some known properties. You're going to have to read across and somehow figure out what the internal energy is. And then you use that for problems. So again, all we're really learning now is how to use these tables. So the question now comes up, which is, how do we know which table to use? There's one more table here, and let me just show you that briefly. This is table A6. So these are all the various subtables. I'll talk about this in more detail later. Fortunately, once we get into the superheated region, aren't pressure and temperature, again, independent properties? Just because we have a particular temperature for superheated steam doesn't mean that it has to be at a particular pressure, right? The temperature and pressure are independent. So temperature and pressure being independent makes things easy for us. We go into the right pressure subtable, like let's say the pressure was, I don't know, how about 50 kilopascals, which is the same as 0.05 megapascals. And let's say the temperature was 150, so here's the 150 line. So we just see where 150 degrees hits 50 kilopascals pressure, and we just read the numbers off from right here. We read the specific volume, the internal energy, enthalpy, entropy, whatever we need. So the superheated tables are really the easiest to use because we don't have to worry about quality. We don't have to worry about one property being dependent upon another. We just go into the right subtable, the right pressure subtable, and pull out the data we want. Now again, we might have to interpolate at times, and I will give you some examples of how to do that. So let me just start talking about, how do we know which tables to use? This is sometimes the hardest part, even though it doesn't have to be. So let's ask ourselves again, how do we know which table to use? Question. By the way, everything I'm talking about here for water applies to the refrigerant 134A in those other tables. It could apply to any thermodynamic, it could apply to any pure substance where we have thermodynamic tables. So everything I'm talking about here simply refers to water, but it doesn't have to be water, right? It could be any of these other properties for any of these other substances. Okay, so let's do this. How do I know what table to use? Well, it depends on what we're given. So let's say if we are given pressure and temperature. Okay, how do we know which table to use? What I like to do is I like to go back to my sketches and using the sketch answer that question for me. So here's our temperature volume sketch, and let's just say that that represents a constant pressure line. And in fact, let's just say that right here, this is the given temperature. So this line right here that corresponds to that horizontal line in the middle of the diagram, that's the temperature we're given, right? Now, if that's the temperature we're given, then clearly this constant pressure line is the saturation pressure that corresponds to that given temperature, right? It's the temperature that determines the pressure if they're not independent. They're not independent. For any one temperature, there's only one possible pressure, right? 100 degrees Celsius will always correspond to 101.325 kilopascals, which is standard 1 atmosphere, always, without exception for water. Anyway, I think that point has been made enough times. So if we're given pressure and temperature, what we want to do is we want to compare the given data to the saturation data. So at the given temperature, if the pressure is greater than the saturation pressure, then what does our phase have to be? Well, let's think about it this way. Our given pressure, if our given pressure is greater than the saturation pressure, that must mean that we're on a line above Psat, right? So where would my given pressure line and given temperature lines cross? Well, they cross over here, right? For a given pressure that's greater than the saturation pressure, but at that given temperature, there's only one possible place for those two lines to cross, and that's here in the compressed liquid region. So if the pressure is greater than the saturation pressure at the given temperature, then it's a compressed liquid. And therefore, we have to use our data in table A7, or again, the approximation we've yet to talk about. Okay, what if the pressure is less than the saturation pressure? Well, the answer should be obvious now, but if we look at the diagram, if we have a pressure less than the saturation pressure, then that would have to be represented by this line I'm writing below. And where would this lower pressure and the given temperature cross? Well, the only place they cross is over there. So if the given pressure is less than the saturation pressure at that given temperature, there's no choice. It has to be a superheated vapor And if it's a superheated vapor, then that means we need to use the data from table A6. On the other hand, what if the given pressure is equal to the saturation pressure? Well, then we have to have a two-phase mixture. There's only one possible pressure corresponding to any temperature. It's called the saturation pressure, and if that's our pressure, then clearly we have a two-phase mix. Again, we can call it a saturated mixture if we choose, in which case we need to use the data in table A4 or A5, depending upon the nature of the data. So this is how we're going to start. We're just simply going to go into those tables. In this particular example, we're going to go into table A4 at the given temperature. We go into A4. Maybe I should have written right up here, since it's the temperature we're given. Use table A4, and again, just compare the given pressure to the saturation pressure. That's going to be how we're going to do it. Anyway, once we know what table to go into, well, then you just go into the table, right? If you're given temperature, and let's say you have another property, which is a specific volume, you can just look it up in the tables. So again, we'll talk more about that shortly. Another thing, again, if we're given pressure and temperature, then another drawing I like to show is the PV diagram. And again, with the saturation region, and let's say that we have a particular pressure that's given. It's that pressure right here. If that's the case, then this line would represent a constant temperature line, and this would represent the saturation temperature that corresponds to that given pressure. So here we'll say at the given pressure, let's use table A5 now, and we want to do exactly the same thing that we just did above. So if at the given pressure, if our temperature is greater than the saturation temperature, where must we be? Well, if the temperature is greater than the saturation temperature, then I have to be somewhere on that line up there, and the only place for the given pressure to cross with the given temperature is way out here in the superheated region. So if the temperature is greater than the saturation temperature at the given pressure, then it's superheated, and we have to use table A6. On the other hand, if the temperature is less than the saturation temperature, so that would mean my temperature line would have to be down here somewhere. The only place where at the given pressure we cross over that temperature, which is less than the saturation temperature, it has to be to the left of the dome. No choice. It has to be a compressed liquid, so therefore it's a compressed liquid. And again, we have to use the data from table A7. And lastly, if the temperature happens to equal the saturation temperature at the given pressure, clearly it's a two-phase mix. And we'd use data from A4 or A5, whichever is appropriate. So this just gives you a little methodology, if you will. Let's call it a test to see which table we use. So we're still not even looking yet at how do we use these tables, but we need to recognize that we do have first to figure out what table to use, then we got to figure out how to use it. All right? Now, this example, or these two examples, were really only to ask us what to do if we're given both pressure and temperature. What if we're not given both pressure and temperature? What if we know pressure or temperature? So if we are given either pressure or temperature and one other property, we always have to be given two independent intensive properties. So what if we were given temperature or pressure and another property? And for this illustration, let's just let it be the specific volume, but it could be anything. We could be given internal energy, enthalpy, entropy. But let's just say we're given either pressure or temperature and specific volume. But again, with the understanding it could be any of those other properties. Well, then what do we have to do? Well, this is actually a little bit easier. Okay, so, yep, thank you. So let's say we're given pressure and specific volume. What do we do here? Well, this is actually pretty easy. If we're given pressure and specific volume, then we just have to go to the pressure table. So we go to A5, our pressure table, and compare the specific volume to VF and VG. All right? So for instance, let's just refer to the diagram that's still here above. This is our given pressure. We know that VF at that pressure represents the left-hand side of the dome, and that VG at that pressure represents the right-hand side of the dome. So don't we just have to check if my specific volume is less than VF? Clearly, we have to be in the saturated liquid region. Compressed liquid region. On the other hand, if my specific volume is greater than VG, then clearly we have to be in the superheated vapor region, right? If we're in between, then clearly it's a two-phase mixture. So given pressure and specific volume, we go to A5, we compare V to VF and VG. If V is less than VF, well, obviously it's compressed liquid. If V is greater than VG, clearly it has to be a superheated vapor. And if I'm in between, then clearly we have to be a two-phase mix. So that tells us what tables we use, right? We use either A7 or A6 or A4 or A5, depending upon the phase, right? So again, this is actually easier. If you're given pressure, just go into the pressure table, compare V to VF and VG. But I did note that if we're given pressure or temperature, so just to continue this, if we're given temperature and specific volume, well, then we have to go to table A4 and do the same kind of comparison, right? We want to compare V again to VF and VG. Clearly, if V is less than VF, if V is less than VF, then it's the compressed liquid. If V is greater than VG, obviously it's superheated. And of course, if we're in between VF and VG, if we're in between VF and VG, then it's two-phase mix. And this can be identified on the TV diagram that we had up there before as well, right? If you want to, you can go back to your TV diagram and you can show, here's VF, here's VG. So clearly, if we're given temperature and specific volume, we just compare it to VF and VG. So again, these just give you some clues as to how to use the data from the right tables. Let me note at this point why we even use F's and G's. And this actually gets back to a comment that I made last week, or maybe it was on Monday. Sometimes in some books, liquids are called fluids, F. Sometimes vapors are called gases, G for gas. So F for fluid, which is our liquid, G for vapor, which is our gas. So it shouldn't be hard to remember what VF stands for, what VG stands for. Now, what about if we do have a compressed liquid? I've mentioned many times that our tables are poor. All right, I can illustrate this. Oh, by the way, everything here also is perfectly applicable to the English system of units. So there's a table A4E, A5E, A6E. It all exists. I just want to make the point regarding compressed liquids. Okay, so here's our compressed liquid table. And you can see that the very first entry in this table is a whopping 5 megapascals. That's 5,000 kilopascals. That's 50 times atmospheric pressure, which is 100 kilopascals. I can't think of any process that is going to be operating only at a pressure that's 50 times atmospheric pressure and then just going up from there to something like 500 times atmospheric pressure at 50 megapascals. So you have the same problem with the English system of units. The lowest entry in the table is at such a high pressure that the table becomes useless to us. Fortunately, it's not a problem. Okay? What we basically write is this. For any property, and I'm just going to use Y as kind of a generic property. And this could be specific volume, specific internal energy, specific enthalpy, or specific entropy. It applies to any. But for any property, we'll call Y, Y at any given pressure and temperature, Y at any given pressure and temperature is approximately equal to the value of that property for the saturated liquid at the same temperature. So I'll call it YF at the same temperature T. So whether it's specific volume or internal energy or enthalpy or entropy, the value of, let's say, the specific volume at any given pressure and temperature, again, as long as it's a compressed liquid, is approximately equal to that of the saturated liquid at the same temperature. Okay. So this can also be illustrated just by looking at the computer over here. Why don't we just take a look at, I don't know, how about 100 degrees Celsius over here, and we'll look at specific volume. At 100 degrees Celsius, at a pressure of 5 megapascals, the specific volume is 0.001041. You can go all the way up to, let's say, 20 megapascals, and it's 0.00103337. It changes by just a fraction of a percent, even though we've increased the pressure by a full factor of 4. So it really doesn't matter what the pressure is. As long as you know the temperature, the value is about the same. Let's go all the way up to 50 megapascals, which is the top of this table. And at 100 degrees, 50 megapascals, it's 0.001020. So it's basically moved from 0.00104 to about 0.00102, even though we've increased the pressure by a factor of 10. So it really doesn't matter what the pressure is. And again, this is an approximation. They're not identical. They're off by a couple of percent. But that's the only choice we really have. If we have a compressed liquid and we don't have the data in our tables, which I guarantee you we generally will not, then we've now proven to ourselves that as long as we know the temperature of that compressed liquid, the value of these properties is going to be more or less the same. So that's what this statement says, right? The value of any of these properties at the given pressure and temperature is about the same as the saturated liquid at the same temperature. So that's how you're going to find your data for a compressed liquid. So now let's start looking at some example problems. And are there any questions on any of this just before I started with the examples? Yeah.
So you said like when it's on a saturation line for either one,
Right.
You count it like completely, like if it's on the liquid side, it's completely liquid.
Well, right. I mean, you can consider the saturated liquid to be kind of a limit, if you will. Think about it this way. Once we had all steam, when the last of that steam has finally condensed into a liquid, that's the saturated liquid line. Or think about the other way. When liquid just is barely beginning to vaporize, that's the saturated liquid line. So it kind of represents our limit.
So my question is like when you were like comparing like the specific volumes, like V small and VF.
Right.
I noticed like you didn't put an equal on any of them.
Oh, okay. It should really have said if it's like here, it should say if VF is greater than, or I'm sorry, less than or equal to. Because, yeah, if the specific volume is exactly that of the saturated liquid, then, well, it's a saturated liquid. You had to be below the saturated liquid to be in the compressed liquid region. So, yes, that's a good observation that there and also back up here, both of these should have really said less than or equal to be accurate. Granted, if it's equal, it's not really a two-phase mixture anymore, but that's okay. It's still a saturated liquid. All right, so any other questions before I move on? All right, so let's look at a series of short examples. Let's say that we're talking about water for all these examples. So the first one will be this. At 200 degrees Celsius, find VF, UF, and PSAT. Okay, so we need to figure out, well, what tables to use. Now this is a little bit easier, right? I haven't exactly said that there's two properties. I've simply said at this temperature, what is the saturated liquid specific volume? What is the saturated liquid's specific internal energy? What's PSAT? It should be entirely obvious just based on the problem statement that we have to use table A4, right? I mean, you're given temperature and you're asked to find saturation data. Where does the saturation data exist? Well, it's in table A4. So it's really just a matter of going to the table and then scrolling down to the given temperature. So here's table A4. The temperature given was 200 degrees Celsius. So it's actually on the bottom of this previous page. And this is where we're going to get all of our information. So the first column is temperature. The next column is the saturation pressure. So PSAT is 1554.9. And this is going to be in kilopascals. So there's one result. The next column is our VF column, right? This third column here, saturated liquid VF. So 0.001157. And that's going to be in meters cubed per kilogram. And then we want to find UF. Well, we just have to go to the right column. So fifth column is internal energy for a saturated liquid. There's UF. So just read down, and it's 850.46. And the units are kilojoules per kilogram. So there's one example problem. Again, you should be able to see how incredibly straightforward it is to get the data out of our tables. It always bothers me when students just never figure out how to use the data tables. They could be the brightest students in the world, but if you don't know where to get the data for the problems at hand, you're sunk. I mean, you have to learn how to use these tables before you even figure out how to use them for problem solving. All right, let's look at another example. We're still talking about water now. So at 4 megapascals, let's find TSAT, and how about some saturated vapor conditions? So how about if we look for VG and HG? In other words, the specific volume saturated vapor, and then the specific enthalpy of the saturated vapor. Well, this time, clearly, we have to use table A5, because that's our pressure table. And we're just going to go to A5, and we're going to scroll down till we get to the appropriate pressure. So we're looking for 4 megapascals. So the pressure column is in kilopascals. So it's not on the first page. Go to the second page. OK, here we go. Now note that these are still in kilopascals, but we know that 4 megapascals is the same thing as 4,000 kilopascals. So we just use the data right off that table. In the second column, the temperature is what we call the saturation temperature, and we get 250.35. Is that right? Yep. So 250.35 degrees Celsius. VG would be 2 more columns over, right? So we go past the third column to the fourth column is the saturated vapor, and just read off the number, 0.049779 cubic meters per kilogram. And then lastly, we want to find the enthalpy of the saturated vapor. So we skip all the internal energy columns. We pass HF, past HFG, and then the fourth column from the end is HG. And again, we just read the number. So the enthalpy is 2800.8 kilojoules per kilogram. By the way, you always want to carry your units through. If you don't put units down on a problem, I'm just going to consider it wrong. Okay, you need units, absolutely. Not only because they're important, they're also going to give you some clues as to whether you solve problems correctly. If you solve a problem and the units don't work out at the end, you made a mistake somewhere, right? You wouldn't know that unless you kept carrying through with all the units, especially in the British system because you've got all those conversion factors. So you always want to write your units. You always want to carry through with them. All right, and then lastly, one more, still for water, at 400 degrees Fahrenheit, let's just find VG. Okay, so do I want to just go back to table A4? Not entirely. It's English units, so you do certainly have to pay attention to the units. We're going to go to the second section here of my own handout, and we're going to go to A4E. Again, A4E is just like A4, but with a different set of units. So we go to A4E. And again, this is real simple. You just go down to the appropriate temperature. So it's past the bottom of the first page. So go to the second page of this table, and it's right up there on the top. Okay. So if I asked you for saturation pressure, you can write it. I guess I asked you for VG. So you just read across, and it's 1.8639. And the units now are cubic feet per pound mass as opposed to meters cubed. And that would be the last example for today anyway. So are there any questions on these simple examples? All right, we've got more simple examples. We're just learning how to use all these tables. I have assigned some homework from Chapter 3, I think problems 23 and 24, to get you thinking about these tables. So that's something you're going to have to do. We've yet to talk about what do you do if you have a two-phase mixture. How do we introduce quality? Quality is something that we'll be talking about right at the beginning of class on Wednesday. I'm pretty sure that the homework I assigned does not require that you know anything about quality. Yes, true. Okay, so quality is something you'll have to use on next week's homework for the following week to be due. So that's all for today. Again, homework from last time is up here at the front. Plus is full credit, check is 2/3 credit, minus is 1/3 credit. Monday's a holiday. Have a nice long weekend.